This is our effort to reinvent the Swift programming language and basically port it to Python. So to take all the good bits that people had in Swift and make them accessible to people that are writing scripts in Python. And before I start, I'd especially like to acknowledge Yadu and Anna, the first two authors there, who have done 99% of the work. Myself, Justin, who's in the back there, and others, we do far less, but we get to stand up here and talk about it. So basic motivation behind Parcel, I guess we hear a few sort of common requirements from people. They have basically a bunch of tools that they want to string together into a pipeline, and they want to run it on various machines, from clouds to clusters to supercomputers. The second thing we hear a lot is, I've got a Python script, or I've got this great Jupyter notebook, it works really well on my laptop, but now I want to scale that and run it on a much larger machine, on a much larger set of data. So that's sort of the two primary use cases we're trying to address with this work, and we're trying to do it 100% in Python so that you don't need to deal with any of these other complexities. So as I mentioned, pure Python, pip install Parcel, that's all you need to do to start using the Parcel programming library. The basic idea is to try and keep Python scripts as Python-like as possible. So essentially what you do is you annotate these functions to make what we call Parcel apps. These apps are sort of either Python functions or wrappers around external bash or binary applications that need to be executed. We then, once you've defined these apps, the control logic, the rest of the Python script, every call to one of these apps will basically decompose that into a graph, working out what the dependencies are between those calls. So assuming that there's no data dependency between two applications or two apps, they can basically execute in parallel. They can execute concurrently, respecting these data dependencies that we create between them. One of the really big advantages of Parcel is that these scripts are independent from where they run. So we're really focused on transparency. So you write your script once, run it anywhere. We don't want to be in the situation where I've got this Parcel script running on Blue Waters, now I need to update it to run on Mirror or Theta or Argon. We want to basically say, let's keep that Python script the same. Yeah, we've got some config issues behind the scenes that we need to tweak. We've got a different scheduler, we've got a different launching model, but that's all abstracted behind configuration files that we can give you for the sort of bigger machines, and for your own sort of smaller machines you can construct yourself. So you see on the right here an example of some Parcel code that you probably can barely see. It's very, very trivial. We'll run through some code in a bit that will probably tell you a little bit more about how it works. So as I alluded to there, one of the big sort of building blocks on which Parcel builds is the idea of futures. I'm sure many of you have seen futures promises in the past. The idea that essentially a Parcel app returns a proxy for the result. So we don't know at sort of when we first invoke it what that result's going to be. We just know that at some point when that's executed, it'll be filled in. And we can then pass that future to the next app, saying, well, the result of this first one is an input to the next one, and leave that to Parcel to handle how we actually schedule these things and run them in parallel. We have two types of futures. Every application, or every app basically returns a future. You can inspect it and see how that app's performed, what the result of that app is, and then data futures, which are essentially mappings to files or objects that are returned from a Parcel app. As I said, Parcel scripts are completely execution provider independent. They're also execution model independent. So as I said, the same script can be run locally on your laptop. You build your script locally and then go and run it on a grid or a cloud or Blue Waters. It works directly with a scheduler, so we don't require like Condor to do these types of things. You can actually combine together multiple execution resources into one Parcel script. So I can be running one on my laptop, running some things on Blue Waters, and also running some things on Theta. We hear that a lot from users. In practice, I'm yet to find a user that actually uses that functionality, but people always seem to think it's nice. We noticed that some of this functionality is quite useful to other people, OSG being one of them, or some groups in OSG. So we actually carved off the lower Python library that speaks to different schedulers into what we call libsubmit, which is available on GitHub. So it's a very simple Python interface, basically submit, cancel, tell me about how my job's running. It's probably a few hundred lines of code for each provider that we support at the moment, which is, as you see there, Cloud, Slurm, Torque, Condor, Cobalt. Feel free to take a look. It might be useful to some of you who are trying to submit things to Torque or other resources, and please feel free to contribute if there's something there that you would like to see that's not yet there. Please add it. We'd love to sort of have that open up to the community. And then, as I mentioned before, we talk about execution models as well as execution providers. So when I'm running locally on my machine, it doesn't make much sense for me to be using pilot jobs. It makes more sense for me to be using threads. When I'm running on a very large machine, we need sort of extreme scale scheduling, such as what SwiftT provides. So we try and abstract this in the Parcel configuration as well. So essentially the same script, we can just change out the underneath sort of execution model of how the actual tasks are executed on a machine. And as I said, the configuration file describes how to use resources. So one thing that I think Parcel, an opportunity that Parcel sort of opens up. So we work a lot with research computing centers, supercomputing centers, and one of the most common, I think, use cases we're hearing from people is this love for Jupyter and this need to try and take my Jupyter notebook and run it at some sort of scale. And I think an obvious solution is, yeah, I can run Jupyter on a login node and I can try and plug together some things, but there's obvious complexity in terms of doing that. I can also run a Jupyter notebook on a compute node, but again, that's just giving me a bigger box to run my Jupyter notebook. So we're really focused on trying to not only sort of allow Parcel scripts to be executed in Jupyter, which sort of happens transparently. I can write a Parcel script, run it in Jupyter, it'll scale out over multiple resources, but also to try and sort of exploit that Jupyter visualization interactive environment. So to try and head towards what we're calling interactive supercomputing. So allowing people to basically have their Jupyter notebook, run things on big resources, support stuff like checkpointing, because people have this habit of shift entering cells and often you don't want to run another million jobs by accident. Trying to integrate with things like the visualization and widget support, so being able to visualize the graph as we're going, because Parcel has sort of a dynamic graph model where we don't know the whole thing in advance, we sort of evolve based on what's spit out of individual apps, and to try and provide sort of widgets for status and debugging, even control. And also in terms of how we can integrate with multi-user Jupyter environments like Jupyter Hub, being able to pass through authentication tokens like what I showed you with the Globus piece, being able to authenticate using a web-based flow, using those tokens then to permit access to a computational resource. So we have some work in Globus to extend the SSH model basically to be OAuth compliant, so you can authenticate using tokens, access tokens to SSH. And so that's obviously very, very useful in the Parcel environment, because then we can have this web-based authentication flow that returns tokens that can then be used to SSH, create a channel into a resource to actually submit jobs. So again, I guess I'm Mr. Jupyter. I came along with some Jupyter notebooks to show everyone. I thought that was going to be the deal today, but I was clearly wrong. I also spent a lot of time, well, not me, Yadu. I spent a little bit of time. Yadu spent a lot of time getting everything running on Blue Waters, and unfortunately, we're not going to be able to show that. But instructions at the bottom on how you can run Parcel on Blue Waters. So fairly trivial: module load, BWPy, pip install Parcel, clone this tutorial repo, and you should be away running. In terms of how you actually want to execute on Blue Waters, so one thing you can do, you can download the code and run it with threads locally on the login node, probably discouraged. You can use these Blue Waters supports Jupyter notebooks, which I think is coming up in the next tutorial or the one following that. So you can spin up a notebook and create an SSH channel into that notebook, so it's running on the login node and you're connecting to it from your laptop. And also Parcel supports a model where you can run your notebook on your laptop, create your own SSH channel to the machine to actually execute things. So again, we have I sort of probably didn't structure this as well as I could, but we have a Parcel tutorial here in the GitHub Parcel repository. We have a tempmb environment, try.parcelproject.org, which will spin up a dynamic notebook that you can all run through. I don't know, again, on the scale of that. Or again, we can use the binder environment to spin up notebooks dynamically. Okay, so GitHub Repo. Bunch of directories here, which is probably not important for what I'm going to show you now. We've got some configs for using some of the resources we use. I don't think we've yet put the Blue Waters config in there, but we should. Some example sort of apps, some shell scripts that you can try and orchestrate into real workflows. But what we probably care most about are these three notebooks here. We'll start with we've probably only got time. What are we at? Yeah, we've only got time for the introduction, but there's also some examples of various workflows implemented in Parcel in a notebook, and also some of the advanced features, which is checkpointing, memoization, caching of apps, basically, and also Globus integration. So as I mentioned in the Globus tutorial, we have this ability essentially to orchestrate Globus transfers as input and output of Parcel apps. So let's fire this one up. Okay, how are we doing with size? Is this visible? Okay, good. So again, all we've done here is we've pip installed Parcel on this, this container. This is probably not great Python to just import star from Parcel, but that's what we're doing to save space. So we'll import Parcel. We're at version 051. The first sort of construct to really understand is what we call the Dataflow kernels. So this is really the brains behind Parcel. This is the thing that manages this dependency graph and works out which tasks can actually be executed at any given time. In order to construct the Dataflow kernel, you have to give it a configuration. These configurations we normally keep in a library sort of alongside the script. So as I mentioned, there's probably some config files in this repository for Argonne resources, UChicago resources, and probably NERSC, and soon will be Blue Waters. So in this case, all we're doing is we're defining a local config that's going to use threads. As I mentioned, if you want to run the following tutorial using pilot jobs or on Blue Waters, just change this config, as I'll show you at the end, but we'll do threads because it's a little bit quicker. Okay. So now we're into, interestingly, oh, I do include different apps. Okay. So looking at, this is still quite small, isn't it? We'll just go that big until we have a problem. The basic definition of how we define an app. So here we've got a very simple hello world app. It's just a Python function that returns a string. We're annotating it with our app decorator that tells us this is a Python function, and we're passing in the DFK. The DFK is actually going from this into a singleton model. And then as a result, we're going to print the future.result, so to actually make that call wait for the future to return to us. So we'll do that. Again, this is just to prove or point out that Parcel apps are just Python apps. You can pass in whatever variables you like. This is an example of multiplying two things together, getting the result. And then the second mode of app, as I mentioned at the beginning, is this bash app, so this external script that we might want to call. So here we're basically wrapping a call to a library, an application, a binary, or a shell script on the system. Essentially, all we're doing in this case is we return the command that we want to run, echo hello world. We have some extra arguments here we can pass to the function to capture the standard out, standard error, in case we want to know what's happening there. So in this case, because we're echoing, it's going to be captured by standard out, so we probably want to look at that file. So we can run that. Okay, what's next in the tutorial? Okay, so the next one is showing us how we can actually deal with files. So we'll first create 3 files, aptly named hello 1, 2, and 3, with hello 1, 2, and 3 inside them. And then we will write a Python Parcel application or script that will concatenate these files. So what we've done is we've defined a cat app there that has a list of inputs and a list of outputs. The command line call is basically just to cat those, whatever we give as inputs, that array, and pipe that into a single file. When we call the cat app there, we're passing in a glob pattern to say just run on all of these inputs, all these hello 1, 2, and 3, and then produce the output file, all hellos.txt. And at the end here, we're going to retrieve the result and print what's in those files. So, sorry, what was that? How does it know that it runs all of them? You mean in terms of multiple, how does it concatenate multiple files? All of them is... Oh, okay. Okay, so I was wrong. This is a single, so this is using, because if I pass to cat, I guess that pattern, cat will respond to that. I didn't look very closely. I thought what we were doing was basically listing the whole array, which you can also do with cat. You can pass in to cat a series of files that will be concatenated. But in this case, we're relying on the command line to just say hello star, anything that matches. So when
this is run, is there any way to track or log which were the exact files in the file that match?
In this case, no, because this is opaque to Parcel. I mean, Parcel sees this as essentially that one file going in. In some ways, this is a bit of a shortcut. So we have 2 models in Parcel in terms of how we deal with files. We sort of have some trickery around dealing with strings. And if you're passing a string in as an input, it's treating it as a file. So it'll think this is probably just one file. But we also have a file construct that I'll come to later. So if you were writing this for real, probably this is a bad way to do it. Probably what you should do is in Python define list comprehension that's actually going to go and create all of the files that you actually want to pass into it, so that Parcel will actually track those dependencies properly. Yeah, exactly. That's basically what this is.
Sorry, a follow-up. So is there any functionality if you want to keep track of all your files, if you're running multiple workloads, is there any way to save these in a database or is there some logging mechanism?
So we have a checkpointing mechanism, which has arbitrary sort of destination where it gets saved. At the moment, it's, I think, only file-based. I don't think we have a database connector, but it would probably be fairly trivial to do that. So these checkpoints will essentially get hashed to a file with whatever the input files that went into it and what the outputs are. Yeah. Okay, so it's good. I've given this a few times and no one's ever, maybe it's changed, I don't know, but no one's ever picked it up on that. It's good. Okay, so futures. So as I showed before, oh, this is going to be, okay, we might go a little bit smaller. So here I'm going to show you how the future model works. So if we're making a very simple app that's basically doing a sleep and then returning hello world, we're going to see the blocking results when we actually try and get the results of that file. So if we make a call to the hello function and put in this app future, we can then ask that app future, is it done? Or we can wait on that app future by explicitly calling the result function. And again, if we check then, is it done? It should be done by that stage. So the first one, is it done? Obviously very quickly, no, it's false. Now we're waiting the 5 seconds for that future to actually be created. We get it, and then done is true. Data futures. So here what we're doing is, again, we're using a bash app, we're sleeping for 5 seconds, then we're going to echo whatever the string is that's given to this function into a file. So this basically shows you the same thing as before. It's sort of hard not being able to show both of these at the same time. I don't think I shift-entered it. Okay, so we're waiting, so that will be it at this bit. We now wait for the result. Here we're calling result on the actual file, so we define these output files to track what the outputs or the results of the function were. So here we're actually explicitly saying, let's get the outputs of that function, let's wait on the results of the first one, and when it's ready, we'll read the contents, which is hello world. Scroll up, okay. I think that's most of the script. So this is part of the future. So you're asking, how do we know that outputs is something meaningful that we can actually do something with? So every Parcel app has this outputs variable, which contains all of the file outputs that are created as a result of invoking it. So I'm probably running pretty short on time, am I? 8 more minutes. Okay. Data management. So as I alluded to before, the sort of shortcut of passing in strings is representative of files is a little bit dangerous. So we have this Parcel file object. The advantage of the file object is that it abstracts location. So we can basically define this file object using a reference to a globus accessible location, an HTTP location, an FTP location, and then basically pass it around as if it were local to the app that's going to run, and Parcel will deal with the complexity of making sure that that physical file is present where that app's going to execute. So shared file system, if you're pointing to a globus file out there in the wild, that'll actually transfer it into the shared file system and then invoke the app using that file when it's ready. So in this case, what are we doing? We're going to copy. So we're going to copy by catting a file into another file. So we're going to take the first input file and put it in the first output file. Where did I find? Oh, first we're actually going to create this file because we don't have it. So I'm creating a file called catin.txt and I'm writing hello world. I'm then defining these two Parcel files, the in file, which is the file we just created, and the out file, which is the file that will be created. I'm then making a call to the copy app, passing in the input file and the output file. I'm going to wait for the results as we did before and then print the contents of it. So this should happen quickly because we're not sleeping in there. So you see that this is basically showing the same type of app as before, but using this file construct, which in this case appears very simple and trivial, but when you're actually dealing with sort of wide area networks or non-shared file systems, this is quite useful to be able to actually materialize files that exist externally. So that's sort of the building blocks of Parcel. The last parts of this demo or tutorial really show how I can link together these apps into these dynamic workflows in which the data dependencies will be observed and control the execution. So in this case, we're going to combine a Python app and a Bash app. This is surprisingly common. In this case, we're going to generate a random number in the Python app using the random function. And then in the Bash app, we're essentially just going to echo whatever string is passed to it into a file. So we're creating a random number and saving it in a file in a rather strange way, but it illustrates the point. So here we generate a function, a random number between 1 and 10. I'm going to print it just so we know what it is, and then we're going to call the save function. And you'll notice here that well, let's get rid of this. You'll notice here that we're not calling result. So essentially that generate app is going to generate a future, which we're then going to pass into the save app, and that save app will only be executed when the generate app is complete. So again, very quickly, that happened very fast. We should probably put some sleeps in here. Sure. I'm going to bring you to every tutorial. Yes. Here. So if we want to see the result of it for message, yes. This function, where we're passing in the future. Well, I printed it out from down here. I'm actually reading it. What's that? Sorry. Oh, so how is this happening? You mean? Yeah. So this is what Parcel's doing. So Parcel's essentially waiting for that future to resolve, and then it knows when that future is resolved how to treat it. In this case, it knows to treat it as a string because it's being used in a string. If that were a file, as input to, say, an open command, it would be used as a file, if you get what I mean. So essentially, it's a shortcut that it knows that by passing in this future, Parcel knows how to handle a future. It knows that within an app, treating it as the future makes no sense. Trying to resolve what that future is into its value makes sense to the app. Yeah, so Parcel itself is resolving those futures within the apps so that they can actually do something. And remember, we're trying to be as unobtrusive as possible. So we're trying, where possible, not to make people change their Python scripts too much. So ideally, we don't want them putting .result in very often. I mean, if you're constructing this workflow, you'll notice there's no results until we get to the end, because we don't want that really to block. We're not putting barriers in there. So that code looks more sort of pure Python. I'm down to 3 minutes, so let's skip these workflows and go to the end. Again, you can run these try.parcelproject.org, so you can run it at home or here. So the last thing I wanted to show you is how easily we can change this configuration model. So as you saw before, we have this thread-based config, where we're essentially saying we're using the threads executor. There's no provider. We're saying use 4 threads. There's some other config here that we won't go into given the time constraints. We can also define a similar config that's going to use pilot job model. So in this case, using Python Parallel as the pilot job model. I was wanting to show you this example using Blue Waters, doing pilots on an allocation that we actually go and submit to the queue. We don't have that, so I'm just going to run pilot job locally, so essentially set up a master and a worker, or a master and several workers on the same node that I'm executing on. We have to give it a little bit of information. There's some constructs here that, again, we don't have time to go into, but blocks essentially describe the shape of the allocation that we're trying to grab. Parcel does some elastic stuff, so it can sort of provision, expand, and retract those blocks depending on what you need. Some wall time. So most of this, again, we don't have time to go into the details, but this is in the documentation. So you'll see I've defined 2 configs. I've defined this IPP config, and I've defined this threads config. So now when I go to run my script, I can change these back and forth. So if I want to run just with threads, which is actually surprisingly common that people want to combine threads and IPP in various ways, to run a simple app where we're going to generate a random number, probably several times, I'm guessing. We're going to then concatenate it into a file, and we're going to add the results of those files. So we'll create 5 files with random numbers, concatenate those files into a single file, calculate the sum of the random numbers. So I'm assuming We calculate 5 random numbers, we then put them in 5 files and have these 5 numbers in that one file, and then we sum it. So if we do this with threads, this will happen very quickly. It's a big number. I don't know what we're random between. And then we can basically go and change this script to use the IPP config, which is going to run pilot jobs. So this would be representative of me developing this workflow on my laptop and then wanting to run it on Blue Waters. I just go and change the config I'm using. This will take a little bit longer because it actually has to spin up this infrastructure. It's concerning. So at the end? So I don't know if in the main code base yet there is like a barrier function, is basically what you're asking. Is there a point that I can say, wait for everything at this point to finish before I carry on? We have that ability back end, but I don't know if it's made available yet. It's definitely coming up in the not too distant future. So that didn't work. I don't know why. I'm assuming this is a temp MB problem because that's worked every other time I've tried it.
Yeah, this question I guess applies either to Dataflow or to the previous one, the workflow. When you write this loop, the like for I in range 5 event, like that looks to me like a serial loop. So can you clarify how, like, where it's sort of knowing to do that in parallel?
So essentially every call here is going to be, it's not going to be executed straight away. So this array is going to be filled with futures.
Okay.
Yeah, so
It's dot result that's doing it.
dot result is forcing that future to be resolved. But if I pass that array of futures to a Parcel app, another app, it's just going to go through them and know their futures and resolve them. So
So like in the simple example above that, the like parallel workflow,
okay, let's have a look.
it's when you ask, it's when you say, I mean, just because that seems to be sort of a common example.
The parallel workflow, which is this one.
It's
Dataflow, one more, parallel workflow.
So you say outputs equals I dot result for I.
Yeah. So this is us explicitly waiting for each one. This is us going through each thing in that array and waiting for that future to resolve and not doing it in a smart way.
So at that point, though, Parcel knows to do that in parallel, basically?
Yeah, so essentially, once we get to here, once we're out of that loop, we've created those 5 calls. Those tasks are all fired off to Parcel to manage their execution. And so if I didn't do result here, they wouldn't be resolved until I actually do that.
That serial loop is essentially like launching them to all of the parallel.
Yeah, exactly, yeah. Yeah, so that's one of the things in Python. We have some, in Swift it didn't work quite that way, but we don't have the same ability, yeah. Okay, I know it's break time, so some people probably want to leave, but I can keep answering questions.
So can Parcel interact with Slurm? Or
Yeah.
what's keeping you from running Blue Waters?
What's keeping you from what, sorry?
You said you wanted to show running this on Blue Waters.
Oh, I could have run it somewhere else, yeah. I could have. I didn't. I could have run it on my UC cluster at university. I didn't think about that. I thought this was going to be easier.
But basically, Parcel can generate the Slurm.
Yeah, it's essentially what it does. So that libsubmit library basically generates, we tell it in the config how big a block size to get, how many nodes to go and request from the scheduler, and then it deploys the pilot workers on those nodes and starts running workload on them. In the either advanced or workflows. Workflows, one of them, I think workflows actually steps you through, the last example steps you through, create one locally, run it with threads, then go to a big machine and run it with IPP, and then use an SSH tunnel to actually run it on a big machine from your laptop. Yeah, somewhere over here. Oh. We're going to break a record for questions. I don't know who was next. I don't actually know. We'll go here.
So do you have to, start up your MPI job, wait for that wait for your job to start, and then run this, or does this put your job in the queue?
It puts it in the queue, so you have to wait. It's another reason that probably showing this running live in a 20-minute tutorial is tough. So yeah, you'd have to wait for that allocation to get granted before you can deploy the worker nodes. I'm just going to go here, then back this way.
So apart from this is written in Python, so how is it different from the Swift?
Justin can probably answer this question. So Python has some, I don't know what the right word is, difficulties in terms of some of the things we can do. So Swift was basically a language ground up, so everything in Swift was parallel. Variable assignment, every single thing was parallel. In Parcel, essentially, we're limited to what we can define with these apps. So that's one big difference. In terms of what you see as a big difference, Swift is its own language that's sort of C-like, right, Justin? Yeah, and Parcel is completely Python. So do you want to say anything else about differences with Swift and Parcel? Okay. Yeah, exactly. Yeah, and our goal was to take, I mean, we knew we couldn't take everything from Swift, but our goal was to take 95% that's actually useful, like that people really need, and bring that to Python.
So the major difference is the language itself.
The major difference to you is the language, yeah. You don't have to learn Swift anymore. You have to learn Python plus a few decorators. Yeah, so hopefully that's a lower learning curve. We're yet to prove that, but if I can do it, then anyone can.
So you basically are kind of launching your job from this Jupyter notebook.
Yeah.
And then it'll go into the queue and maybe start.
Yeah, and maybe start, yeah.
Close my browser and like walk away, like how would I get my answers?
Yeah, so that's a good point. So at the moment, we have no resiliency beyond checkpointing and checkpoint files. So we do write on task completion essentially to the checkpoint file so that we can restart from whatever was completed, but we don't have like a database based like fault tolerance resiliency model for start the script, save whatever state we are of the DAG, run or not run, and then come back to it. So
So if you close your window, it's like going to kill your job?
yes, exactly.
That's it. So you have to have, that's the critical thing. So you have to keep your laptop
Yeah.
active the entire session of the job, because the job might take like a day to run.
Yeah, you'd probably want to do it in screen or something if you're on a remote machine. Certainly don't want to keep your laptop open for a day. I mean, this.
You have to run it out of a notebook to begin with, right?
No, you don't. Yeah.
Submit the Python.
Yeah. Yeah. So sorry, there's no dependency on Jupyter. I'm just all in on Jupyter. I don't know. I don't even fully believe that Jupyter is as good as people say. But
You can log in and then
yeah.
run it there and then leave.
Yeah. Exactly. Yeah. So this has been a good learning experience. This tutorial. We need to make some of these things clear when we present. But certainly no dependency on Jupyter. It's just nice for showing a tutorial, I think.